All right, for those who are logging in here on Zoom, we're going to start off with the assessment stuff, and those you'll need your camera on for that. When we're done with those, if you feel like turning off your camera, that's fine. But while we do the assessments, you'll need your camera on. For those here in class, I'll be handing out potential paper copies of the assessment if you want to fill that out. If you want to fill it out on Zoom instead, you're welcome to do that as well. I don't really care, whatever you prefer. So you can either, or no, it's not on Zoom, on Canvas, right? You can either log into Canvas, fill it out on your phone or laptop if you feel like it, or paper that will be handed out in class. Yeah, those on Zoom here, you have to turn on your camera. If you're able to point it towards your computer, please do so. If not, figure it out. But we'll get started on these questions on Canvas in just a minute. Okay. So, you know, you're getting credit for taking these assessments. So, you know, while you should normally not cheat, also please don't cheat on this. It's not really going to improve your grade by cheating. So I prefer you just please don't cheat. You know what I mean? Those in person, those on Zoom, right? It's not going to help your grade any by cheating on this. So don't cheat. So then the department can get an accurate assessment of things, point of these exams. Okay. All right. Riley, if you want to hand out the scientific methods at first assessment, I can help try to hand those out as well. Okay. Those on Zoom, if you want to take it on Canvas, you're going to need the passcode, which I will put down here. I need to change something in chat. So passcode is science quiz 94. Okay, so capital S, capital Q. So right, to manually zoom in here, right? So science quiz 94 on Canvas. Okay, for those who are getting paper copies right here in class, will be the front and back. Quizzes, so look at this. Okay, but yeah, so you'll go to the scientific method assessment on Canvas, right? For those who are on Zoom, go to the scientific method assessment. You can find all of the assessments under the module tab, under the assessment module, right? So first, that scientific method assessment. Again, the ID for that is science quiz 94 here. Those in person, start doing that. I will start the timer here. Okay. So you have like 10 minutes for these 5 questions. Okay. Again, there are questions on the back page of the piece of paper that you got coming in. That's on Zoom. On Canvas. And those on Zoom, please turn your camera on. I don't know, just the requirement I was given for doing this told people have to have their cameras on. So you can remember to do the front and back. We need more time. Class. Okay, so for those on Zoom, the next communication quiz. For that, the passcode is COMM capital Q I 94. Did they somehow print less of that one than the other ones? All right. Hopefully not. Let's see if I have. Again, COM quiz 94 is the passcode with capital C, capital Q. No more? Oh my gosh. It must have ran out of paper or something. Shoot. Do I have? Where's? Is there? How many people don't have it? Quite a bit. All right. I mean, you can if you want. Otherwise, I will. What we can do is, if someone's willing, is someone not written on theirs right now, or I'll pull it up. Just give me a second. I will pull up the file itself. Just have it on the screen here in just 1 second. So sorry about that. So I guess if you have like a piece of paper or an extra piece of paper or something else, you can write it down on. So I have one person on Canvas here saying that they can't see some of the pictures on the communication quiz. Uh, Please let me know if anyone else is having that issue. Trying to see what the issue might be, or if it's just a local thing. It's on my end or not. All right. For those on Zoom who are ready, the next will be the teamwork individual. So this you'll do on your own, and then next I'll break you guys out into groups to work on it together. For that, the passcode, just teamwork one, teamwork one, okay? And right over here, start passing out. So again, hopefully I have enough black and white. Thank you. All right. All right. So again, right, do the teamwork individual assessment, teamwork assessment individual, right, with the passcode teamwork with capital T, all one word, right, and then the number one. Again, that you'll be working on with yourself. And if you go to my screen, you can see that the different passcodes for the different quizzes. People here on Zoom, just let me know again if you have any issues. I'll do my best to try to resolve them. Right, and as a reminder, these assessments are all purely extra credit towards your quiz grade, so it's all extra. All right, so for those on Zoom, what I'm going to do is I'm going to create breakout rooms. I'll just create like 3. You can work on it with people in that breakout room, and it's going to be the exact same question. Okay, so it's going to be the teamwork quiz group, right? And so for that, the passcode is teamwork 2. Again, so let me create breakout rooms real quick. I'll create like 3 breakout rooms. I'll have it assigned automatically. Okay. And you can discuss with the people in your room about the question and, work on it together if you like. Okay. So all the rooms are open. So go ahead and go in your breakout room, discuss. When you're done answering, you can pop back out and leave your breakout room. Okay. Thank you, Daddy. You can now talk whoever, however. Okay. All right. So for those in class here, pass your quiz with your names to the center, and I'll collect them. For those on Zoom, if you don't want your camera on, you can turn it off now. A wave of cameras goes off. Okay. If you have any further questions about them, I'll try to answer them real quick. But otherwise, we'll get going with class. All right. Okay. So seems like any further kind of questions and things like that. I'm going to do. So today we're just kind of wrapping up chapter 17 and mainly we're going to just do a couple more examples because we kind of covered up all of the, let's see here, so let me share screen. Yeah. All right, so the chat, you can now chat with people publicly and privately on Zoom. Let me turn on the screen here. Class. All right, so all that for titration. Where were we? Solubility. Talked about those conditions that affect solubility. Talked about that last time. Talked about complex ion formations. Okay. So yeah, so I believe we ended, if I recall right, we didn't do this example yet. So this is where we'll start today. Okay. Chapter 17 examples. We'll talk about these, do an example now of, right, last time we kind of finished up talking and saying about how, right, the solubility of a salt can be affected by other things in that solution. For a number of salts, it can be the pH. Okay. And so here's an example of a, you call it salt or weak base, right? Cesium hydroxide here that has an equilibrium constant 1.5 times 10 to the minus 20, right? And we can look at what is the solubility of that salt, right, in water versus in a solution that contains 0.1 molar sodium hydroxide. Okay. Right. And again, all of this is related with this discussion of solubility of salts in solution, right, which is an equilibrium problem. Okay. And so right, that exact same question right here, right? So again, for these KSP problems, right, these equilibrium problems, right, we need to think about our equilibrium reaction, CeOH3 going to Ce3 plus aqueous plus 3OH minus aqueous ions, right, where this guy on the left is a solid, okay, right, which this has a KSP, right, expression is going to equal what? Is that KSP equal, not numerically, right, but the expression for it?
CE minus 3, CE plus 3, and then 3 OH minus Q.
Yeah, OH minus Q. There you go. Yep. So right, it's an equilibrium constant, right? So it's always products over reactants, ignoring solids and liquids, right? CeOH3 is a solid, so we don't even bother including it. So you're just left with the products, right? Which is Ce3 plus times concentration of OH minus, raised to their stoichiometric coefficients, which happen to be 1 for the cesium and then 3 for the hydroxide. Okay. So that's our KSP expression for that equilibrium reaction, right? And so our questions are, what is the molar solubility of the salt in these two different solutions, right? So in A here, right, I'm just pure water, which means, right, in the solution, I add some amount of salt, right? That doesn't really matter, right, because the solid doesn't appear in our equilibrium, but I have some amount of the salt that I add, right? And when I do that, right, I'm not going to start off with any concentration of cesium or hydroxide, right? And I'm going to get some amount, right? So I'm doing an ice chart here, right? I'm going to get some amount of the cesium and then 3 times that amount of the hydroxide in solution for when this cesium hydroxide breaks apart, okay? And so the equilibrium concentrations are going to be X and 3X, right? And again, the 3 here is because of that stoichiometric coefficient in our balanced equilibrium reaction, 3 OH minus, right? And again, the thought process, right, when setting up these problems, right, you put some solid in a solution. That solid can break apart into its ions, right? And so initially, I just have solid in the solution. But again, it doesn't tell you how much you initially put in because it doesn't really matter, right? Because it doesn't appear in the equilibrium constant expression and things like that. So as long, right, as I put in just some solid, it's going to be fine, right? So we just kind of ignore the solid, just focus on the ions, right? The things that are dissolved in solution. And for both of those, I start off with none in the solution, right? Because I just have pure water, just have H2O, right? That's the only thing floating around in solution, H2O. Okay. And so this is my equilibrium concentrations, and so I can just plug it in to my equilibrium constant expression here, right? I have, right, KSP itself is 1.5 times 10 to the minus 20, right? That's what KSP equals. That's what we're told. And that equals concentration of cesium ions, which is X in an ice chart, times concentration of hydroxide ions, which is 3X cubed, right? And so this right side simplifies down to 27X to the 4th. And again, that equals 1.5 times 10 to the minus 20. Okay. So any questions kind of so far about what we did, why we're doing it, how we're doing it? All right. All right, and so, oops. And so what we need to do to solve for X, right, is I need to divide both sides by 27. And then I will take the 4th root of both sides, right? I mean, if you do that, you'll get X to the 4th equals 0.0556 times 10 to the minus 20, okay? And so then you take the 4th root, right, of both sides in order to find that X equals, so what's the 4th root of that? 4.85 times 10 minus 2, that's 5. 6, I believe. I did that right, yeah. 4.85 times 10 minus 6. Trying to make sure I did the math right. 5, 8. Yep. So I believe that should be correct, right? So this, right, is X, which, right, X represents the concentration of Ce3 plus, ions in solution, right? 4.85 times 10 to the minus 6, right? Right, so that's the concentration of cesium ions in solution, right? Which is the number of moles of cesium ions that were dissolved, right, in, say, 1 liter of water, right? So then what is the molar solubility, right, of CeOH3 given this? Right, how many moles of CeOH3 can I dissolve in 1 liter of water?
Dissolve 4.85 times 10 to the negative 6 moles.
Yep. So the molar solubility, okay, solubility of CeOH3 is just 4.85 times 10 to the minus 6 molar, okay? Right, and the reason is again, the molar solubility, right, is how much of my compound can I dissolve to reach the saturation limit, right? The saturation limit is when you establish equilibrium between your ions in solution and the solid, right? That saturation limit is given by the equilibrium concentrations of this ice kind of equilibrium problem, right? So the equilibrium concentration of cesium is the saturated amount of cesium ions in solution, right? Which, because it has a stoichiometric coefficient of 1, and in our equilibrium reaction here, cesium hydroxide has a stoichiometric coefficient of 1, right? 1-to-1 ratio, right? That means, right, to form a saturated solution, I dissolve 4.85 times 10 to the minus 6 moles of CeOH3 in 1 liter of solution to form, right, this concentration of 4.85 times 10 to the minus 6 molar cesium ions, and 3 times the amount for hydroxide ions, right? But so our solubilities, right, again, the molar solubility of a compound, right, the solubility of a compound is what is the concentration of that compound that forms a saturated solution, right, which a saturated solution, again, is a solution that is in equilibrium with the ions and the solid, right? And so, again, that's how solubility is related with equilibrium, okay? The solubility of an ion, or sorry, of a salt, right, is related with its equilibrium concentrations, okay? Right, so in general, for these type of problems, the X that you're solving for is typically, I'm not going to say 100% in every single problem, but typically X is that solubility, right? Happens to be, okay? Right, so questions about how we solved this? Yeah.
What would be the situation if it wouldn't be X in solubility?
What would be so if I had an ion that like was so for example what Ca3PO4 2, so that's PO4. Okay, this salt, when it breaks apart, the solution forms 3 calcium and 2 phosphate, and so right, it's not a 1-to-1 stoichiometric ratio between any of the ions in solution and the solid. So you'd have to like divide by 2 or divide by 3 or whatever, however you defined X. Well, actually, so it depends, right? If you set it up kind of like this, where it's X times the stoichiometric coefficients, then X should always be your solubility, actually, right? So if I were to set up an ice chart with this, and I had, equilibrium reaction or whatever, and I did, 3X and 2X as the equilibrium concentrations that I get out from this, then X would still be my solubility, my molar solubility. So as long as you kind of set it up where it's X times the stoichiometric coefficients, that X is going to be your molar solubility. So, other questions? Oh, sorry, I completely moved that all the way down. All right, so for part B, okay, for part B, I have this exact same equilibrium reaction, exact same scenario, but now H minus, right? But now when I'm filling out my ice chart, right? Again, cesium hydroxide, I don't really care, doesn't appear, right? I still have no initial concentration of cesium, but now I have a 0.1 molar solution of hydroxide, right? Because 0.1 molar sodium hydroxide is a strong base, so that sodium hydroxide will fully dissociate into sodium ions and hydroxide ions, right? So I have an initial concentration of 0.1 molar OH minus, right? So again, I'm going to have X plus 3X here. Its equilibrium concentration is going to be X, okay? Now here, the equilibrium concentration of hydroxide, I would say, is 0.1 molar plus 3X, okay? Well, without any hydroxide in solution, right, that concentration was a very, very small number, right? 10 to the minus 6, right? Be 10 to the minus 5 for hydroxide after you multiply that by 3, okay? But so it's a very, very small number, okay? And so we're going to use the approximation that this is just roughly 0.10 molar, okay? So the fact that 3x plus 0.1, when rounded, is just 0.1, okay? And when we solve for x, you'll see that this is still a very valid approximation, okay? Right, this is similar to like the approximation we use for Ka and things like that, and those problems, right? Kind of appears here in KSP, where again, our equilibrium constant's a very, very small number, okay? And so this concentration, my initial concentration of 0.1 is much greater than this equilibrium constant. So this should be a very valid approximation, okay? And so then my KSP equation, 1.5 times 10 to the minus 20 equals X times 0.1 cubed, right? Concentration of OH minus is 0.1. Concentration of cesium is X, okay? And so in this case, X equals 1.5 times 10 to the minus 17 molar, okay? Which again, this 1.5 times 10 to the minus 17 is the molar solubility of cesium hydroxide, right? And so we see comparing between a pure solution of water and a 0.1 molar solution of sodium hydroxide, right? That solubility has significantly decreased, right? Okay. Right, because you already have some of the product in solution, right? So this equilibrium, for it to be established, is going to end up having a very small concentration of cesium, right? You're going to have very little of that left, right? Okay. So questions about these problems, right? Again, these are equilibrium problems. I see an equilibrium constant, right? I already think equilibrium problem, ice tables, right? Relations between equilibrium concentrations and plugging those into the equilibrium constant expression, okay? Using this guy and the equilibrium values in my ice chart to solve for whatever I need to solve, okay? Questions about how we did what we did? And okay, so finally, the last kind of topic to talk about with this KSP, just talking about the idea if you have some solution with a bunch of ions in that solution and you want to ask yourself, will these ions precipitate out and form solid, or are they at equilibrium, or is it forming an unsaturated solution? And to do that, we just calculate the reaction quotient Q, right? Which again is the exact same expression as the equilibrium constant K. I'm just plugging in non-equilibrium values, okay? And if Q is greater than your equilibrium constant, that means that precipitation is going to occur, right? That you're going to form some more reactants and use up some of your products, okay? and you're going to form some of that solid until you eventually get Q equal to K, then it will stop, right? Because if Q is at K, you're at equilibrium, and there's going to be no net change in the concentration of your ions and the amount of solid in the solution. And then if Q is less than K, right, then you can dissolve even more solid in that solution, right? You have an unsaturated solution, okay? So Q less than K is unsaturated. Q equal to K is a saturated solution. Q greater than K, I guess you could think of it as like a supersaturated solution, right? Where you're going to then crash out a bunch of solid, right? Get a bunch of solid to form till you get to a saturated solution. Okay. All right. We haven't talked about this in any of the previous questions just because, right? We haven't done an example where we have some initial concentrations of the ions for both things. Okay. Okay. So questions about that idea, this concept, right? What we need a reminder what Q is, right? And so I could easily have a multiple choice question, right, where I tell you like this is the concentration of this ion or that ion in solution, right? This is the equilibrium constant, the KSP, for the salt that they form, right? Does this ion form more solid? Does it form? Can it absorb more solid, right? Is it saturated, unsaturated, right? Is this at equilibrium, right? These type of questions could be asked. Okay. All right, so this last kind of numerical example here, right? The solubility product for GDOH3 is 1.8 times 10 minus 23. If a solution of 0.01 molar GD3 plus ions, if you have a solution, right, that has 0.01 molar GD3 plus ions in that solution, and you slowly increase the pH, right, at what pH will GDOH3 begin to precipitate? Okay. And so that's the question, right? Right, and so if we imagine, right, what you're doing, right, when you increase the pH, right, that's increasing the concentration of OH minus ions, right? Because right at very low pHs you have a very acidic solution, you have a very high concentration of H plus and a very low concentration of OH minus, right? So as I increase the pH gets larger, concentration of OH minus gets larger, right? And so in this problem, we have these GD3 plus ions floating around in solution. I'm slowly adding more and more hydroxide ions into solution until eventually I add enough hydroxide ions into solution that solid GDOH3 is going to start forming, right, and precipitating in the solution. Okay? So that's conceptually kind of what's going on here. And so the question is what is that point in which that precipitate starts forming? Okay, right, and that precipitate is going to start forming when we reach, right, the point right before it starts forming is when we reach equilibrium, right? Equilibrium is that saturated limit, right? The largest concentration of ions I can have in solution is the equilibrium concentrations related with your KSP, okay, for your salt, okay? So that is going to define what's the largest concentrations of OH minus ions I can have in solution, which will then determine the pH, right? Because any concentration above that, right, any concentrations above that give me the equilibrium constant, right, I'm going to form solids, right, because then Q will be greater than K, and I will start forming solids, right? And so this question basically is what is the pH, right, that gets you at equilibrium, and any pH greater than that will start forming solids. Okay. Right. And so what we want to be trying to solve here is for GDOH3. Okay, we have our equilibrium reaction, GD3 plus, right, plus 3OH minus, right? Okay. Right, and so we have some initial concentration here, 0.01 0.01 molar, right? Okay, and adding, right, and so, right, like the previous part B here, right, when I start off with some kind of fairly large concentration here compared to the KSP, right, the equilibrium concentration of here is basically going to be 0.01 molar, right? That's not really going to matter, right? ICE, right? There's going to be some change here, but it doesn't matter, right? This concentration is not really changing, okay? Right, because we haven't formed solid, right? What we're wanting to know is, right, what is the concentration of OH minus that I need to have, right, at equilibrium, in order for the concentration of OH minus times concentration of GD3 plus to be in equilibrium, right, to give me the fact that KSP, which equals concentration of GD3 plus times concentration of OH minus cubed, right? I want my concentration of OH minus to reproduce my equilibrium concentrations, because any concentration above that will start forming solid, right? Any concentrations greater than your equilibrium concentrations will start forming a solid, okay? Right, and so plugging in here, we have 1.8 times 10 to the minus 23. This equals our equilibrium concentration of GD3 plus times that of OH minus cubed. Okay. And so x cubed equals 1.8 times 10 to the minus 21. Right. So if you take the cubed root of this, look at that, x equals 1.2 times 10 to the minus 7. More. So that is the concentration of OH, okay, x here, right, which is that concentration of OH at equilibrium, right? So this, right, 1.2 times 10 to the 7 molar, right, is the concentration of OH minus that gets me to equilibrium, right? Any concentration greater than that means that my, any concentration greater than that means I'm going to start forming solid, okay? But the question here is, right, at what pH? So we got to calculate the pH, right? So this is 1.2 times 10 minus 7 equals OH minus concentration. And so we take the negative log of that and then add 14 or subtract 14 or whatever to get the pH, right? You'll get the pH equals 7.08. Okay. And so basically at a pH that is greater than 7.08, you will start forming solid in the solution. Any pH less than that, and you will not. Okay. And at a pH of 7.08, you will form a saturated solution for the solution. Yeah.
Why would it be x instead of 3x?
Why would it be x cubed?
No, like the part.
Oh, why not 3x here?
Yeah.
So I didn't do 3x mainly because, right, how like I started setting up the ice table and then I realized the problem is this problem isn't set up like this, right? I don't have any solid initial, right? So in this problem, I'm not, right, in the previous problem, I started off with some solid and it's dissolving. So all the moles of, that were getting added to solution of cesium and hydroxide were being added from the solid. So it's based off this balanced chemical reaction as to where they're coming from, right? In this problem, right, I'm increasing the pH by doing whatever, right? Adding adding a base to the solution or something like that, right? So the concentration of hydroxide is changing, is being increased by adding like sodium hydroxide or something like that. And so it's not from this breaking apart to form these ions because I don't have any of the solid in the solution to start with, right? And so, yeah, so really I'm just concerned about what is the concentration of OH minus that reproduces an equilibrium solution, right? A saturated solution, And so I just kind of care about x here, right? Right, if I did 3x, right, then I would just have to take my answer and multiply it by 3 to get the overall concentration of OH minus in solution, which is what I'm concerned about. So yeah, so you could have done 3x here as long as you said the concentration of OH minus was 3x, and you would have gotten the exact same answer. So, yeah, I just did x here because right, I knew I wanted just what is the concentration of OH minus that needs to be to create a saturated solution, which is a solution at equilibrium. Okay, and so that's what we solve for, right? And again, this x is the concentration of OH minus. Take the negative log of that, you'll get the POH, and then you take 14 minus the POH, and you will get the pH. And so that's how I got the pH of 7.08, right? And so again, that is any pH greater than that is when a solid will be forming in solution. Any pH less than that, and you're in an unsaturated solution. Other questions about this problem? Let's see here. Oh, so we have some extra examples here. So try to run through one of these two examples. So there's two examples here. The answers of these are already online. The detailed answers are not, but kind of just the final answers are. So I can go through at least one of these in class. So this first one, we have right a 0.1 molar solution of sodium fluoride that we're going to slowly stir into a solution that contains 0.1 molar chromium and 0.1 molar calcium, both of which form a salt with fluoride, right, with different KSPs. And the question is which salt precipitates first? Okay. This other example, right, is you have a solution of cesium that you mix with a solution of iodate, IO3, okay, that can potentially form a solid. And the question is this mixture going to form a solid? Will a precipitate form or not? So I don't know if anyone's curious about first or second example. Well, takers, I'll do the second one. The first example is a lot like the previous one, okay, where you need to find out what is the concentration of fluorine that causes a precipitate of CrF2 to form. What's the concentration of fluorine to form a precipitate of CaF2, right? And then whichever concentration is the smaller is the one that's going to precipitate first, right? The second one is kind of related with the comparison of Q and K, right? Right, and so for this, right, what I'm interested in is what is Q, right? Q meaning the concentration of Ce 3 plus times concentration of IO3 minus cubed, right? Now in this problem, we're mixing two solutions together, which they're different volumes are being added. I'm adding a 750 milliliter solution together with a 300 milliliter solution, okay? And so in total, my total volume, right, is going to be 1.05 liters, okay? Oh, not 05, sorry. Yeah, 1.05 liters, yeah, that's right. 1.05 liters, okay? 750 milliliters plus 300 milliliters gives us, 1,050 milliliters or 1.05 liters. Okay, and so I need to get the new concentrations, right? I'm diluting these two things, right? So the concentration of cesium, okay, is going to be related with, right? So the nu times V nu, right, is like this M1 V1 type thing, right? The old concentration of cesium 3 plus, old, right? Right, so plugging in these type of things, right? This is 1.05. This is the concentration we're looking for. And then the old volume is 0.75 times the old concentration of 4 times 10 to the minus 3. Okay. And then similarly, right, and so I solve for the concentration of cesium here, right? And I do the same type of thing for IO3, okay, which is 1.05 times concentration of IO3 equals 0.3 times 2 times 10 to the minus 2, okay? So again, I'm taking the volume, the initial volume and the initial concentration of IO3, which comes from potassium IO3, and I'm dividing it by the new volume, okay, which is the total volume of 1.05 liters, okay? And when I get those concentrations, I just plug it into Q here, and then I ask myself, is Q greater than K, equal to K, or less than K, right? Okay, so I don't have those numbers off the top of my head, but I can plug them in for those who are curious. But I'll just kind of end here because we've essentially run out of time. But yeah, so on Wednesday, we're going to start thermal chemistry. Okay, videos for that have already been kind of posted. The quiz for this chapter is due by Friday at 10 p.m. It's going to be open by Thursday in the afternoon, the exact time, okay? But there will be a quiz on chapter 17 on Canvas that will be open Thursday afternoon and closed by Friday evening, okay? Again, we'll start chapter 18 tomorrow. Don't forget to turn in your participation questions for the day when you leave on the back table. If people have questions about this example, I'm happy to finish it. Yeah, that's kind of annoying that the colored one just, yeah, they use it in a different printer. In the chem office, they have one printer for colored and one printer for black and white. I guess the colored printer just, you know.
All of the color printers are out there.
All right, thank you.